In today's class, we will see some applications of Gauss law. We can use Gauss law to find out the electric field. So today we will see field due to an infinitely long straight uniformly charged wire. Infinitely long straight uniformly charged wire. This is basically a derivation. So in the exam they'll ask questions like this. So I'll give you the question and then we will see how can we solve that. Use Gauss law. To derive an expression. Use Gauss law to derive an expression for the electric field due to a long straight wire of linear charge density lambda coulomb meter. Use Gauss law to derive an expression for the electric field due to a long straight wire of linear charge density lambda coulomb per meter. So this is the question how they can ask. We will try to solve this. So given you have to derive an expression for the electric field due to long straight wire. So we will consider a long straight wire. Consider a long straight wire. Long means it is infinitely long. Long straight wire carrying charge plus q on its L length. Consider an infinitely long straight wire. Okay. So given, let the linear charge density be lambda coulomb per meter. Let the wire carries plus q charge on its length L. Let the wire carries plus q charge on its length L. So charge density, linear charge density is lambda. That means lambda charge density is q by L, or charge q is equal to lambda L. So total charge will be lambda into L. Now we need to assume because we want to apply Gauss law, we have to assume a Gaussian surface. We have to imagine a Gaussian surface. So for that, what we will do is, first let us consider this long conductor. Consider this long conductor. So this is infinitely long conductor. So I am drawing this much length. and having charges, uniform charges. Plus q we have assumed. So let us assume we need to find out the electric field intensity at a distance r from it. Let electric field intensity is to be obtained at a distance r from it. So distance r is, so let me say some distance r. Let me say this is the point, okay, with a distance r from the wire. Now because the wire is very long, and assume that we are very far away from both of its ends, so this end, it will go up and this will go down. Because it is infinitely long, we cannot draw infinitely long, so I have drawn a short wire. Because the wire is very long, let us say that this point r, we are standing here, and it is far away from both of its ends. So field lines which comes out of this wire, they are all radial and they will lie on the same plane. So the field lines will be like this. The electric field lines. Because the wire is very long and we are far away from its ends, the field lines are outside this wire are radial and would lie on the plane perpendicular to the wire. Therefore it is we can assume a cylindrical Gaussian surface. So I will write here, since magnitude of E is same at every point, which lie at the same distance from the wire. Same distance from the wire. Assume a cylindrical Gaussian surface. Since magnitude of E is same at every point which lie at the same distance from the wire, comma, assume a cylindrical Gaussian surface. Cylindrical Gaussian surface. Let this cylinder has a radius of r and length L. Assume a cylindrical Gaussian surface. Let the cylindrical Gaussian surface has a radius of r and length L. let the Gaussian surface cylinder, let this cylinder be of radius r and length L. So since magnitude of E is same at every point which lie at the same distance from the wire, assume a cylindrical Gaussian surface. Let this be of radius r and length L. Let this cylindrical surface be of radius r and length L. Now let us assume a Gaussian surface. So you assume a cylinder of radius r. And length L. So this side also it has to be r only. And sorry. So this has to be cylinder of length L and radius r. Here also it has to be cylinder, okay? Cylindrical surface. So r and so cylinder. Now so in while applying Gauss law we consider small area. So let us say we are considering a small area here. So let this area be ds1. In this the electric field is radial outward, so this is the field direction, and ds1 will be in this direction. So the angle between ds1 and E is 0. Similarly we will assume another area on this two plane surface and one curved surface. So here E and ds are in the same direction. ds2 and E are in the same direction. The angle is 0. Similarly we will assume another surface here. E is here and ds3. Now angle between E and ds1 is 90 degrees, so cos 90 is 0. Angle between E and ds3 is also 90 degrees, so cos 90 is 0. So we have to consider only this area, curved surface. So total flux phi is equal to integral of surface integral of E into ds, which is equal to surface integral of upper plane face so if you consider upper plane face, E into it is ds1 and the angle is cos 90 plus curved surface E into E into ds2 into cos 0 plus lower plane surface. There are three surfaces for a cylinder. Lower plane surface. So this is E into ds3 and the angle is again cos 90. You can refer back to the picture, so you will know why cos 90, cos 0, and so this angle is 90, and if you consider this curved surface, the angle is between E and ds is 0. So now this will lead us, so this term will become 0 and this term will also become 0. So now I can write 5 is E into ds, because cos 0 is 1. So phi flux is equal to integration of E into ds2. And we know the area, surface area of a cylinder is 2 pi RL. So ds2 integration of ds2 is 2 pi RL. That is the surface area. So, and the magnitude of E is same. So I can write E into 2 pi RL. And flux we have calculated as E is flux is E into 2 pi RL. And by Gauss law we have flux is equal to, so by Gauss law flux is equal to Q by epsilon naught. So this Q by epsilon naught, Q we calculated as lambda L divided by epsilon naught. So this is one equation for flux. Equate 1 and 2, you will get the electric field. Flux is E into 2 pi RL, and also by Gauss law flux is Q by epsilon naught. Substitute the value of Q, that is the total charge, lambda is the density. So E into 2 pi RL is equal to lambda L by epsilon naught, or E is, now cancel here the terms, L get cancelled. So E is equal to lambda by two pi R into epsilon naught. E is lambda by 2 pi R into epsilon naught. And it is directed normal to the surface of charged wire. The direction of E is directed normal to the surface of charged wire. So E is equal to lambda by 2 pi R epsilon naught. So the electric field depends upon the value of R, at what distance you are calculating it.